Welcome, everyone. Welcome to our 9:30 a.m. session, Efficient Computing for AI and Robotics. We're joined by Dr. Vivian See, who is an Associate Professor of Electrical Engineering and Computer Science at MIT. Welcome, Vivian, and thank you for joining us.
All right, thanks, Irina. So I'm very happy to be here today to share with you some of the work that we're doing at the intersection of efficient computing and AI and robotics. So in particular, we know that AI and robotics are very exciting these days, it's very exciting applications. But if we take a look at where the computing is happening for that right now, most of the processing is happening in the cloud. But there's many compelling reasons why we might want to move this compute from the cloud to the edge. So for example, if we want this technology to be accessible to people around the world, we want to really reduce its reliance on the communication infrastructure. So moving the compute to the person themselves will be helpful for that. Another thing is for a lot of these applications, especially in the AI space, it often involves data that is private and sensitive. So for example, in healthcare. So as a result, rather than moving the data to where the compute is happening, we'd like to move the compute to the data or where the data is being collected, so into the device. And then finally, if we think about interactive applications, for example, self-driving cars and robotics, we often are very sensitive to latency or basically reaction times, changes in the environment. And so you can imagine if you're driving quickly, your vehicle's going quickly down the highway, it might not have enough time to send the data to the cloud, wait for it to be processed, and then come back. So in this case, again, you'd want to move the compute into the robot itself. So these are the many reasons why we want to move the compute into the edge device or robot, but there are challenges associated with this. One of the main reasons is the fact that the computing often for these applications is very expensive in terms of power consumption. So if we take a look at self-driving cars as an example, it collects a lot of data from its sensors, but you typically will be burning, like, for example, over 2,000 watts if you use kind of general purpose computing to just process all the data that is being collected at the sensors. And this will require things like wasted heat and water cooling to manage this. So this can be quite cumbersome. And then you can imagine that this is going to be even more challenging as you start reducing the size of the device to, let's say, a handheld device or a portable device, for instance, your smartphone or a smaller robot. Right? Typically, these smaller devices have even much tighter power constraints due to the heat dissipation. So typically under a watt. And unfortunately, existing processors, it becomes very challenging to deliver that for these particular types of applications. So another challenge that we're actually facing is also that transistors themselves are not getting more efficient. So if you look over the past, few decades, the reason why we've gotten these faster, smaller computers is due to things like Moore's law that gives you faster and smaller transistors, and Dennard scaling, which gives you more efficient transistors. But we can see that over the past decade, this has really slowed down. So if we want to meet all of these computing demands, we really have to find some other solution. We can't just wait for better transistors. In fact, what we need to turn to is moving from general purpose processing to designing very specialized hardware for these given application spaces. And this can offer significant improvements in both speed and energy efficiency. And this is one thing that we might want to consider in the context of other kind of energy efficient strategy that we could potentially take. So we can imagine for cross-layer design, one particular approach is to take a cross-layer approach to enable energy efficiency. You can start out with efficient algorithms, making the algorithms themselves more energy efficient. Then the next thing you might want to do is come up with new architectures, right? So how do you build these new computers from the ground up to make them more energy efficient? We also want to look at building new circuits to make them more efficient. So once you define these computer architectures, how can you actually translate them into improved circuits? And then how do you integrate these circuits into more efficient systems? If we're going to redesign the hardware, we really need to think about where the energy and power is actually going. And the interesting thing here is that it turns out that it's not just the computation, like doing the adds and the multiplies, that dominate the power consumption, but it's also the data movement itself. In particular, if you want to do an add or a multiply, the delivery of the inputs to the multiplier and the adder is really what dominates the energy consumption. So you can see down here that this is the energy breakdown across some computations, like multiplications and additions from different precisions. And you can see really down here that the data, the movement or reading data from some kind of local memory, let's say on the actual computer, or reading the data from off-chip memory, off of the computer, these consume significantly more energy than doing a multiply and add itself. And keep in mind that the scale here is in, is an exponential or log scale, so it's much more significant, right? So we're talking about orders of magnitude more energy to move the data around. And so if we're going to actually try and build systems that are energy efficient, we really need to address this issue of moving data around the system, not just doing the arithmetic computations. And then the challenge, of course, is that we start looking at applications like autonomous navigation, they tend to use a lot of data, right? So for example, one of the first things you need to do in autonomous navigation is understand your surroundings. You might, capture with the camera on your vehicle, capture the scene. And what you want to do is semantic understanding, which is basically understand, does this pixel represent the ground? Does this represent, the sky? Does this represent a person? That's what referred to semantic segmentation. Often you have to process this at very high frame rate, particularly if you're moving very quickly. You may need a larger resolution so you can see, people or objects that are far away. And then finally, you might not want to be able to, detect people at different scales. And often this means that, changing a HD image, which is 2 million images, you might have to, have multiple different scalar versions of it, which is going to increase the size by 1 to 2 orders of magnitude. So that's a huge amount of data right there. The other thing is, often as you're navigating, you also need to build a map and you need to be able to see, how far away the different pixels are. And you can imagine as you are traveling further and further, the size of the map is going to grow. Okay, so this is an additional challenge that you might face. And so in kind of the first task, what we want to do is just kind of tackle how do we build efficient systems when there's a huge amount of data. One of the very first tasks that you do in autonomous navigation is just to basically figure out where you are and what you're facing. So for example, you can see here, there's, this is a camera that's mounted on top of a robot or a drone that's flying around, and you're trying to estimate, shown here, where you are in the 3D space and where you're actually located. And so one way of doing this is what we call visual inertial localization. It's basically fusing camera information with IMU information. So this is like accelerometer and gyroscope data to get this estimation of where you're located in the 3D space. If you're navigating in an unknown area, you might also have to build a map of your of the region or the environment that you're actually in. So we want to be able to do all of this at very low power. And so what we were able to do is to design very specialized hardware to do this localization at under 25 milliwatts. This is in collaboration with Surtesh Kerman, who's another faculty here at MIT. And this is basically the first chip that does complete visual inertial odometry on chip. So it does all the front end processing of the camera with feature tracking and detection, and also some of the processing of the IMU information, and then some optimization to fuse the accelerometer and gyroscope data with the image data. And so here's the chip that we actually designed. It's 4 millimeters by 5 millimeters. You can see it's pretty small. You can mount it on these very small drones. And it only consumes, as I mentioned, under 25 milliwatts, and it can still operate in real time, up to 171 frames per second. And when you compare it to a general purpose mobile or desktop CPU, you're talking about 2 to 3 orders of magnitude lower energy to do this. So how do we actually achieve this? And so in addition to building specialized hardware, what we want to do is we want to make sure that all the processing is integrated onto the chip itself, onto the computer, because we know that moving data on and off chip is going to be very expensive. We kind of saw before that a DRAM access is very expensive. If you're going to integrate everything on chip, you also have to make sure that it's not like a lot of stuff you have to store, because even moving data around on chip is expensive. So we do things that like apply low cost image compression and also exploit sparsity in the graph and linear solver. And so as a result, all we need to do all this processing, we need under a megabyte of data that is stored on chip. Okay. Another thing that we have to talk about if we're going to talk about AI and autonomous navigation is deep neural networks. We know that deep neural networks have become really the cornerstone of AI. It's given us record-breaking, state-of-the-art accuracy in a wide range of applications from vision to speech recognition, gameplay, medical, and in fact, it's found in a lot of applications that we use today. We also use them also in robotics in terms of understanding the environment. So for example, you can imagine a task like depth estimation where I'm given an image and trying to figure out how far away the objects are, or like semantic segmentation, as we mentioned, labeling the class of each pixel. And so yes, all state-of-the-art approaches use deep neural networks, but the key challenge here is that deep neural networks require several hundred millions of operations and weights to compute. And so when you compare it to something that's very ubiquitous, like video compression, which you all have on your phones and actually we're using right now, you're talking about 2 orders of magnitude or more complexity to do deep neural networks as compared to something like video compression. So, one of the key challenges is how do we make neural nets as ubiquitous as video compression? How do we make deep neural networks much more efficient? Well, there's certain properties of deep neural networks that we can exploit. So one is that they actually exhibit very high parallelism. So they do a lot of these multiply and accumulate operations that happen in parallel. So high throughput is possible, very high speed is possible. The key challenge, which should be no surprise, is the memory access. That's the key bottleneck, right? So for every multiply and accumulate you do, you need to read in 3 values and write 1 value. So that's 4-to-1 ratio in terms of memory access to compute. And if you read these from, off-chip memory, which is much more expensive, it's going to be, 200 times more costly in terms of energy per read compared to the compute itself. So if you take, a popular neural net, like let's say AlexNet with 700 million max, you're talking about 3 billion DRAM accesses. So this is going to be very expensive. But there's also some properties that we can exploit in terms of input data reuse, meaning that we can read some data in and then use them for multiple operations. So you don't have to read it every single time from this very expensive memory. In the context of DNNs, you have properties like convolutional reuse, where the pixels and weights are going to use multiple times just for different operations. We also have image reuse, where we apply the same filter to the multiple filters to the same image. So each pixel in that image is going to be reused multiple times across the different filters. And then finally, we have filter reuse. If you process more than 1 image at a time, usually we process like a batch of images, then a weight and the filter can be reused multiple times across the different images. And then the idea is that you want to design some specialized hardware that allows you to exploit this reuse property. In particular, what you might want to do is design specialized hardware that has, very small memory close to the processing engine. And the reason for that is a small memory, we're talking about under a kilobyte, is going to be very cheap in terms of energy and doesn't have to move very much. And so just to give you an idea of how the energy compares, to do, let's say, a multiply and accumulate, and let's say that's 1x in the AL to do that computation, reading from this tiny memory, but 1K byte is going to be super cheap as well. It's about the same amount of energy. Reading from a larger memory, let's say a buffer of like 500K bytes is going to be 6x the energy, and then going off to DRAM is most expensive. So in general, farther and larger memories consume more power. So what we want to do is we want to try and, read as much as possible of our data from this small memory. So we, read the data once from this expensive DRAM and then keep on reusing that piece of data and reading it from this register file as many times as possible to do many operations. Now, the problem, of course, is that this small register file memory is very tiny. We have these large, million, billion weight-sized DNNs. So what we need to do is you need to, chop up your very large neural network into small pieces so that it fits in this register file. And then the question is, what is the order at which you're going to process all of these teeny tiny pieces so that you could maximize the reuse, so you don't have to read so frequently from the DRAM. And that's exactly what we kind of explored in some of our work. In particular in the IRIS work, where we try to really optimize the ordering of how we process the data. We call that the data flow. And this allowed us to exploit data reuse and drop the amount or reduce the amount of memory accesses by 100x from the global buffer, from the larger buffer, and by over 1,000x from the off-chip memory that's very expensive. We actually went ahead and fabricated this chip, and then we measured the power. When you compare it to a mobile GPU, you're talking about an order of magnitude reduction in energy compared to that GPU. I also want to just mention, we talked about, AI, robotics. There's also important applications of AI in the healthcare space. And so this is some work with Thomas Health at MIT. And one of the key, things that we're trying to tackle is dementia. So we know that, diseases like Alzheimer's affects lots of people, 50 million people in the world today, and it's projected to continue to grow, unfortunately. And one of the key challenges in assessing these types of diseases is that doing an assessment, typically you need to go and see a specialist, and they're going to ask you a series of questions or maybe ask you to draw a clock. These assessments can be very time consuming. And so as a result, you can't go very frequently, and it's not very accessible to many people. In addition, even with the specialists, there's often going to be it's a very qualitative assessment. So there's going to be a repeatability issue. So, those of you have probably experienced going to different specialists, they might have a different result. So the question is, can we make this more quantitative and make this more accessible? So one of the areas that we've been looking at is that, which has been actually very exciting, is it's been shown that eye movements themselves can give you a quantitative assessment of the severity, progression, or regression of these particular diseases. So for example, based on your eye movement, you can tell whether or not a certain, if your Parkinson's medication is working or not, for example. So this has been a promising area of research. And so the question that we had is, can we kind of enable this type of measurement to happen on the phone? Right now, this type of measurement still happens in the clinic, but if we can enable it to happen on the phone, for example, it can happen, at home at a very low cost. You can collect a lot more data, and then this data can help assist the specialists in terms of having a better assessment of your cognitive state. Okay, so as a summary of what we're talking about today, in general, we want to enable energy efficient AI. We really want to extend the reach of AI beyond the cloud, just get out of the cloud. And this is really a critical step of making AI ubiquitous. And then the key way of enabling this is a cross-layer approach. So yeah, there's alarm before, so you might not have heard, but really not just looking at the algorithms, but also looking at the hardware and looking at them across the entire stack. And this can really help us push the energy efficiency of AI so we can make it ubiquitous and accessible by all. And this is going to be critical for the progress of AI over the next decade. And so, these slides are also available on our website if you want to check that out. Some other resources on this. So this is a really growing and emerging area. There's been a lot of research in this space. So recently we completed a book on this particular topic. So if you're particularly really interested in learning about how to efficiently process deep neural nets, both from a hardware perspective as well as an algorithmic perspective, I invite you to check out this book. Another thing is we actually run a class typically it would be on MIT campus, but this year is going to be obviously virtual and live for MIT professionals who are very interested in this topic. So actually the registration of this course is already closed, but if you are interested in it, we will open up some slots for this particular conference or attendees of this conference. So if you're interested in learning more about this topic, I invite you to send out an email to the shorts programs at MIT by tomorrow to sign up for the class. The class starts next week. And then finally, we've had a lot of tutorial material. This is just a small short snippet of the research in this space. If you're interested in doing a deeper dive, either in the neural networks aspects or the robotics aspects, I invite you to check out the variety of talks that are available on our website. And with that, I want to thank you very much for your attention. And I'm happy to take some questions.
Thanks so much, Vivian. So we do have a few audience questions. Here's one from Anonymous. So Anonymous is asking, is specialized hardware the only answer? Is there any hope for the huge installed base of compute, mobile or embedded out there to use deep neural networks?
Yeah, so certainly I think you can get a lot of savings from trying to come up with much more efficient algorithms that might be agnostic to the hardware, right? So even just thinking about when you're, designing these algorithms for AI and robotics, making, jointly thinking through energy and accuracy can bring you quite far. So actually, we've also looked at research in that space, just, for example, how to make the network smaller, but still maintain accuracy. But you can get even better if you jointly design those algorithms with the hardware itself. So then the hardware can really exploit interesting properties of the algorithm. So just to give you one example, one way that you can efficiently design this also is that you make the algorithms, let's say, sparse, meaning that there's a lot of zeros in there. And so we know that anything times 0 is going to be 0. So if you can have the hardware recognize that and avoid doing the computations where one of the inputs is 0, that's going to make it much more efficient. And I would take it even further. There's also been research of also not just optimizing the hardware architectures, but jointly optimizing the devices, so the transistors that might feed into these architectures as well. So there's this whole area of called processing in memory or in-memory computing, where you bring rather than putting the memory by the compute, you bring the compute into the memory itself, like really making the compute into the data. And in that case, once you start bringing things into the memory, you need to often redesign the devices of the memory itself so it can also do computation.
Great, thank you. So we have one audience member who's asking if you would mind going back to the slide with the links to talks. I think there's some interest in further exploration. And while you're doing that, another question from David. So, and this one's about waste. So even if edge computing requires less energy than it does require more, does it require more physical resources, and does it therefore create more electronic waste? Is that, is this physical waste in addition to energy something that you're considering in these calculations?
I think that's a great question. I mean, I think if you want to take a step back and think about just like carbon footprint, there's carbon footprint in terms of like the energy, the carbon that you're emitting through the computation itself. And then there's like the capital expenditure of like fabricating all these devices. I think it's certainly worthwhile to think through in terms of those types of trade-offs. Certainly, I think it's important to not create waste. And ideally, I think if people should utilize whatever products they have to the best that they can. I think you could actually also think about, often the stuff in the cloud, they also there is a timeline for that as well. And I think it's just a matter of changing behaviors and not, excessively using different things.
Absolutely, that makes sense. And so if we're thinking about, making the best use of all the resources that are available, we just got another question. Do you have any thoughts on leveraging efficient edge compute devices and cloud compute? So how would you design systems by thinking more holistically?
That is another fantastic question, right? So I think, again, you might want to think about where should you be doing the computing? Should it be at the edge or in the cloud? And I think it really depends on your particular application. It's just another thing to also keep in mind that commuting to the cloud is also very expensive, right? So it doesn't come for free, and there's a lot of energy and carbon that's dispensed for doing that communication. I think it really depends on your application. So for example, if you're doing kind of real-time things, as we mentioned, you have very private data, then maybe on the edge is more appropriate. However, if you need to process very large data sets, you won't have that storing on your device, so then maybe going to the cloud makes more sense. So it really depends on your application, but it's an open area of research in terms of how do you balance where the compute should actually be based on the requirements of the system, and also based on the energy consumption and carbon emissions.
Thank you. That makes sense. And so going sort of into the nitty gritty of the kinds of models that you're choosing, another anonymous asker wrote, in many cases, we find ensembles of models like gradient boosted trees plus DNNs provide better answers than just DNNs alone. By optimizing for DNNs, are we penalizing other models? And how do you consider that in your model creation?
Another great question. So I would say, I think hopefully this is up. So if I go back to like the work that we did on visual inertial odometry, that's actually not DNN based. It's actually just the more traditional pose graph kind of factor graph optimization based approach. So I think it's really important to not think that DNNs is the be all and end all of everything. There's a lot of challenges with DNN. They're computationally expensive. They require a lot of data. And then also they have interpretability issues sometimes. So I think really trying to pick the right algorithm for the right application is really, really important for those multiple reasons.
Thanks. Let's see. So any other questions coming in? You know what, since we're on the topic of the nitty gritty, so Rich asked early on, for embedded computing like robotics, why not use a more neuromorphic or analog model like True North, or always on mixed analog digital? Any thoughts on that?
Yeah, so I think it depends on what you're prioritizing. I think the first thing I personally always start with is to make sure that the quality of result, for example, the accuracy is there for your given application, and then look at the hardware. I think one of the challenges in neuromorphic approaches is the ability to show that high accuracy. And then once you have that high accuracy, can you then come up with more efficient hardware to support and maintain that accuracy? Because if you can't, get from point A to point B, then it doesn't really matter in terms of what hardware you're looking at. Now, in terms of analog computing, as I mentioned or hinted towards that, in-memory computing, where you bring compute into the memory itself, involves a lot of analog types of processing. And so there's a lot of pros and cons about that, as I mentioned. So you can do a lot of analog computing, but then you're also sensitive to non-idealities. And if you need to transition from the analog to digital domain, there's that kind of conversion challenge as well. But I think it's an open area of research that people are actively pursuing. And as I mentioned, there's a lot of exciting research in the space of co-optimization or co-designing of the devices, as well as kind of the, in this case, like the memory architecture as well, which is a lot of the analog, where the analog sits.
Fantastic. Well, thank you so much, Dr. C. This was an extremely thought-provoking talk, and we really appreciate your time. Attendees, thank you for joining us, and thank you for insightful questions. And another friendly reminder that if you want to continue discussion, there is a link at the bottom of the presentation page for information for joining our Slack channel, where you can continue the conversation with our presenters and with community members. And if you want to join us for our next talk, go ahead and join us in 5 minutes for our 10 a.m. talk through the link. And thanks again, Dr. C.
All right, great. Thank you very much.